All right, today we're diving into this kind of hidden world of cryptography. And no, we're not talking about those giant servers that power the internet. We're talking about the tiny, almost invisible computers that are literally everywhere, stuffed into your credit card, your car keys, you name it. So this all kicks off with a really tough puzzle, one that experts have been wrestling with for years. How in the world do you build a lock for a device that has almost no processing power and a teeny tiny battery? The usual security we have on our laptops. It's just way too heavy, way too demanding. And figuring this out, it's absolutely crucial for the connected world we're all living in. Well, the answer is a whole new kind of security, something we call lightweight cryptography. And right at the front of the pack, there's this one design that really changed the game. It's a lightweight cipher called Ascon. Okay, so let's get into the tiny security problem. The real challenge here, and this is important, isn't just taking our existing encryption and hitting it with a shrink ray. No way. It's about building something new from the ground up. Something that's crazy efficient, but doesn't give up an ounce of the tough-as-nails security we all need. I mean, we are literally talking about billions of these tiny resource-strapped devices all around us. Things like your IoT gadgets, smart cards, even medical implants. And car key fobs, the little systems in your appliances. For something like a medical implant, a security failure could be a life or death situation. All these things have barely any processing power or battery life, which makes those big traditional encryption methods totally useless for them. So faced with this massive global challenge, what do? Well, the U.S. National Institute of Standards and Technology, you'll hear them called NIST, they set up this huge multi-year competition to find the absolute best design out there. And after a ton of intense testing and evaluation, they picked a winner. And that winner was Ascon. Now, Ascon isn't just one thing. Think of it more like a whole family of cryptographic tools. Every single piece of it was built from scratch with one goal in mind: be super secure, but also super efficient on those tiny little devices. Okay, so in this Ascon family, there are few members, but two of them are the ones you'll hear about most. First, there's Ascon 128. That's for what we call authenticated encryption. It doesn't just scramble your data to keep it secret, it also makes sure nobody's messed with it in transit. Then you've got Ascon-Hash, which is all about creating digital fingerprints to prove your data is the real deal. For most of these lightweight jobs, these two are the go-to choices. So how in the world does Ascon pull this off without needing a supercomputer? Well, the core idea is actually pretty clever and surprisingly easy to grasp. It's all based on a design that cryptographers know really well, and it's called a sponge construction. Yeah, seriously. The process works a lot like a kitchen sponge. First, you initialize it, kind of like getting it ready with a secret key and a unique starting value, a nonce. Then comes the absorb phase. You feed your data into the sponge one chunk at a time, and it gets all mixed up inside. And finally, you squeeze it. The secure output, your encrypted text or a hash, gets squeezed right out. It's a simple idea, right? But it's so elegant and really, really efficient. But what's actually happening inside the sponge? What's going on during that mixing phase? Well, that's where the real magic is. The data gets put through this incredibly intense scrambling process called a permutation. Just think of it like shuffling a deck of cards a million times a second. It makes the data totally unrecognizable. Okay, so this whole permutation thing happens in rounds, and each round has 3 basic steps. Step 1, you add something called a round constant. This is just a unique number that gets mixed in each time to make sure the process never gets repetitive or predictable. It's a simple way to stop some basic attacks right in their tracks. Next up, step 2 is where we substitute some bits using something called an S-box. This is the only part of the process that's non-linear, which is just a fancy way of saying it's designed to create confusion. The whole point is to completely hide the connection between the original data and the scrambled output. It makes trying to work backwards pretty much impossible. And finally, step 3 is all about mixing those bits up. A diffusion layer spreads all the changes from that last step all across the entire chunk of data. This creates what cryptographers call an avalanche effect. It means if you change just one single bit of the input, it causes a massive cascade, and about half of the bits in the output will flip. It's a really powerful way to make things secure. All right, so the design is pretty clever, but here's the million-dollar question. Is it actually secure? I mean, Ascon didn't just pop up out of a lab one day. No, it went through years of intense public grilling by the best cryptographers on the planet. So for its main version, Ascon 128, it uses 12 full rounds of that three-step permutation we just talked about for its most important jobs. That's 12 complete cycles of adding constants, swapping bits, and spreading everything around. It's a lot of scrambling. And here is the part that really shows you how strong this thing is. After all those years of people trying to break it, the best attack anyone could come up with, well, it only managed to break a watered-down version of Ascon that used just 7 rounds. They couldn't even get close to the full 12. So that gap, that huge space between the 7 rounds that attackers could barely break and the full 12 rounds that are actually used, that creates what the designers call a generous security margin. It's basically a massive safety buffer, and it's why everyone feels so confident that this thing is going to be secure for a long, long time. Okay, so let's tie all of this together. Why should we care about a tiny, elegant algorithm like Ascon? What does it actually mean for our daily lives? Well, what makes Ascon a total game changer is its unique mix of features. It's tiny, right? Small enough to fit on the smallest chips, but it's also really efficient and fast, even on big CPUs. It's flexible, using that same core permutation for both scrambling data and fingerprinting it. And maybe most importantly, it's designed to be resistant to side-channel attacks. That's where attackers try to steal secrets just by watching how much power a device is using. Ascon helps shut that down. What this all means is that strong, modern security isn't just for powerful computers anymore. It's not a luxury. Thanks to Ascon, it's now accessible for pretty much everything. It's out there protecting our smart homes, our infrastructure, and all the personal stuff on the devices we rely on every single day without killing their batteries. And that's the story of Ascon. Its success is just a great reminder that sometimes the biggest breakthroughs really do come in the smallest packages. Ascon has cracked the code for securing our tiny devices. And that just leaves us with one big question to think about. What's the next great frontier for cryptography?